Alright, so we're still doing 3.1 exponential functions, and this is going to be part 2. Our central questions are, what does an exponential function represent? And what are the characteristics of a graph of an exponential function? So the natural base e. The number e is defined as the value that 1 plus 1 over n raised to the nth power. So it approaches as n gets larger and larger, so as n goes to infinity. The approximate value of e is 9 decimal places. So e is about 2.718281827. You don't have to memorize that number. The irrational number e, approximately 2.72, is called the natural base. So the function f of x equals e to the x is called a natural exponential function. So, on your calculator, you want to try the problem e to the 3.2. So I've pulled up my calculator, and we're going to do e to the 3.4. So I'm going to hit second. Well, let's clear this first. So second, ln, 3.4. So your answer should be about 29.96. So now we're going to try a problem that involves your natural e. The exponential function f of x equals 1066 e to the 0.042x models the gray wolf population of western Great Lakes. F of x. So that's the population f of x. X years after 1978. Project the gray wolf population in the recovery area in 2012. So 2012 is 34 years after 1978. We're going to substitute 34 in for x. So that means we're going to have f of 34 equals 1066 e to 0.042 times 34. We're going to plug that into the calculator and see what we get. So we have 1000 66 e raised to the 0.042 times 34. So your answer is about 4,445.59. So it's about 4,445.59. Can you have 0.59 of a wolf? No. So you have the population is about, you want to round it, so it's about 4,446 wolves in 2012. That would be your answer for that. So the next thing we're going to talk about is formulas for compound interest. After T years, a balance A in an account with principal P and the annual interest rate R, your R has to be in decimal form, is given by the following formulas. You want to write these two down. So n compounding periods per year, and for continuous compounding. So if you have n compounding periods per year, your formula is A equals P times the quantity, 1 plus R over n raised to the n times T. And for continuous compounding, it's A equals P to the P times E to the RT. Make sure you write this down or take a snippet. You will want these formulas. So we're going to look at an example. This one is about compound interest. So we're going to use compounding periods per year. So the sum $10,000 is invested at an annual rate of 8%. Find the balance in the account after 5 years, subject to quarterly compounding. So since we're using quarterly, that means 4. So N is going to be 4. So we're looking for A. You invested $10,000, so that's your P. 1 plus, and our rate is 8, so that's 0.08 because we want it in a decimal. N is 4. And your time is 5. So if I were to simplify 1 plus 0.08 divided by 4, I would have 1.02, and 4 times 5 is 20. So if I were to plug this into the calculator, I'd have 10,000 times 1.4859, and it would continue. So you would have about 14,859 and 47 cents. So we're going to use the same information, but this time we're going to use continuous compounding. So we're still looking for A, and we still invested our $10,000. E, and our rate is going to be 0.08 times our 5. So if we simplify this, you could plug it all into the calculator, but I'm going to simplify it quickly. So it should be E to the 0.4. Now if I plug this in, we'll have 10,000 times 1.4918, and that will continue. So this means you will end up with about $14,918.24. So that's how much money you would have after your 5 years. So in this case, which is better, compounding quarterly or compounding continuously? So if we were compounding quarterly, we had about $14,859.47. If we're compounding continuously, we had about $14,918.24. So in this case, compounding continuously is a better choice. So make sure you complete the questions below and complete your homework assignment, and we'll see you in live class.